we're going to start taking a look at how we're going to use Matlab to help us define partial derivatives in Matlab. And we're going to be able to find second partials as well as mixed partials as well in terms of f sub xy and maybe fxyx or fxxy, those sorts of things. One basic command that we need to know is the diff command. And you might remember that from the first set of videos that we looked at. And we were able to find derivatives in terms of one variable or as a function of one variable. But let's say we have a function of two variables that we want to try to find the derivative. Well, we have a second parameter in the diff function, and the second parameter is going to define which of the two variables or which variable, if there's more than two variables, that we're going to go through and try to find the derivative with respect to. We have to make sure we define variables that's symbolic. So if we have more than x and y, if we have a function of 3 or 4 variables, then we have to make sure that our sims variables are explicitly stated. And then just to find the first partials, we could use diff of, if we define z to be the function, then z comma x, z comma y. If we wanted to find the second partials, then we go through and say diff z comma x comma 2, and that would find the second partial with respect to x, z comma y comma 2, which would find the partial with respect to y, the second partial. If we wanted to find fxy and fyx, we kind of have to use intermediary steps. So we're going to first find fx by finding the first derivative with respect to x, and then find the derivative of that answer with respect to y. And we could do the same thing with y. Or with yx, excuse me. First, we find the derivative with respect to y, and then we assign that to fy, and then we find the derivative of fy with respect to x. And so I'm going to show you examples as to how to find both the partial derivatives as well as the second and third partials of these different functions. And these are our familiar functions from our first two videos in this section. So let's go ahead and define some symbolic variables, x and y, and let's go ahead and define also, because I'm looking at the problem, we need fxyx. So let's say fx, and then also fxy, because we're going to need to take the derivative of those, and it never hurts to define them as symbolic, even though we might not need to. Right. Now we have our function, which I'm going to call z, and z is going to be equal to the square root of x squared plus y squared. And to find the first partial with respect to x, I'm going to say fx is going to be equal to diff of f with respect to x. And I'm going to say fy is going to be equal to diff of f with respect to y. In fact, it should be z, not x. So I'm going to call it zx and zx, zy. And so we're just going to go ahead and execute this. And I know we still have to find fyy and fxyx. All right, but we just run it, and here we go. All right. The only difference between the two partials is the numerator. One has an x, one has a y. That's a result of the chain rule, right? So we can verify our answers. And this is a good way for you as you're working through problems analytically to make sure you're on the right track with your partials. We need to find fyy. So I'm just going to say fyy is going to be equal to diff of z with respect to y, second order or second partial. And we'll just go ahead and execute that. And the last line will be our second partial, which is much uglier than the first one, because now we have to use a quotient rule or turn that into a product rule. Now, we're going to have to kind of be sly as to how to get to fxyx. All right, so we already have fx from before. So I'm going to say fxy is going to be the derivative of fx with respect to y this time. Now I'm going to suppress that because that's not really what we want. We really want fxyx. Okay, so because we want fxyx, we're going to say that's going to be equal to the derivative, so diff of what we just got, fxy, with respect to x now. All right, and that doesn't need to be suppressed because we're trying to find fyx, and that's what we want to see. The only reason I suppress this is because we don't really need this to be shown. We just need it to be able to get to the answer. All right, so we're just going to go ahead and execute this. And here is our third partial, fxyx. Here's our second partial from before. And pretty cool that MATLAB does a good job in simplifying this a little bit for us. Right? Now, here's the really good news. Now that we've set up this code, we can just go ahead and just literally change a few letters and get the partials for our sine x squared y squared. So I'm just going to change square root into sine. And we're going to execute this. All right, and here we are. Here are the four partials that we were asked to find: fx, fy, and again, notice that fx and fy look similar because there's just one difference of a chain rule. All right, and you'll see that with a lot of functions that have the interior x squared plus y squared or interior xy sort of structure. Now, fyy is a little more complicated because we have to use a product rule. And fxyx is complicated again because we have to use product rule, chain rule, just like we did for fyy. So pretty cool that we're now able to find partial derivatives and check our answers using MATLAB. Now, in the next video, we're going to basically take everything that we've seen so far with graphing and derivatives, and we're going to be able to find the equations of tangent planes, but also to be able to graph those equations of tangent planes along with the original function on the same three-dimensional plot. So pretty cool that we're going to start to see what everything looks like in the next video.